Hi, my name is Scott Marshall, and I am a member of the SCEC Science Planning Committee and the co-leader of the Community Modeling Group at SCEC. And I want to thank the SCEC leadership for inviting me to talk to you today about the community fault model and some of our challenges and progress over the years. First thing I want to point out that we have some new web-based tools that are fantastic. You should all go to the SCEC homepage and check them out, but I'm going to highlight those tools throughout this talk. At the beginning of this meeting, you might remember there was an earthquake and a lot of chatter in the Zoom window about which fault that was on. Well, at the CFM homepage, there is a link to the CFM Association service, which will send you emails to tell you what the most likely CFM fault was for each event. So if you want more information about that, go to the CFM homepage. It's a pretty cool tool. I've been getting emails for it, and it works really well. A model like the CFM requires a lot of different people contributing different things. So I have to give thanks to the SCEC's IT and software team, especially Mei-Wei Su, who's been the primary developer of these new web-based tools that we have. And also CFM developers, Craig Nicholson and Chris Sorling, who've provided many of the surfaces in CFM 5.3, as well as were key contributors to the metadata and the naming system of the structure. So start at the basics. What is the CFM? Well, the CFM is a three-dimensional representation of fault surfaces onshore and offshore in California. The current model, the preferred model, has 440 surfaces, but we also provide alternatives. These surfaces are based on basically any data we can get our hands on. Even though the model is 3D, many times people just want a simple trace map. So we have fancy trace maps like this available at the website. But if you think that's too fancy, then we got you covered. We got simple basic maps of fault traces as well there and several in-betweeners. So again, CFM homepage has all of this stuff. It's not uncommon for somebody to come up to me and say, USURF, CFM, aren't those the same thing? And the answer is no. The USURF is based partly on CFM, and both of these models are based partly on the USGS quaternary fault database, but they're very different. You can see plots of them up here. The Q-faults database is very detailed, and the USURF model is smoothed compared to those. These all have different purposes, and they're all good in their own right. I just want to make sure that everybody recognizes that we're going to be talking about CFM 5.3 and that it is a distinct product from these others. So how I'm going to focus this talk is by laying out some challenges that we faced and then discussing our progress on those challenges. What you can see over here is a screenshot of our web tools with seismicity. And so as an example, you might think, well, can't you just use seismicity? So here I've changed the background layer to aerial imagery. And we're going to zoom in on an area that rhymes with Smidgecrest. You might know it as Ridgecrest. And here you can see the Ridgecrest sequence from 2019. This is the, if you mouse over this, you'll see that's the 6.4 event. And this is the 7.1 event. You might think, well, can't you just make a 3D model based on the seismicity and focal mechanisms? Well, you can, and we did. But what about Garlock down here? The Garlock fault has very diffuse seismicity. You can't really define a three-dimensional fault surface with this little amount of data. So how do we do this? Well, I'll give you an example from Hubbard et al. 2014 of the Ventura-Pettus Point fault system, which is down here in the transverse ranges. If we zoom in, you can sort of see the South San Cayetano fault and the Ventura fault. How was this representation made? Well, what Judith Hubbard and others did is they took all of this disparate data, seismic data, cross sections, industry well data with dip meters, resistivity logs, and they put it all in 3D using CAD software and fit a surface to it. This is built by hand, it's manual, it's time intensive, it's not possible to automate because these things have to be interpreted by a human being, and error estimates are really not possible on surfaces like this. But I would argue that this is a very good way to make a fault model because it includes the most different types of data that we have. But recognizing that this is very difficult to do on a large scale, semi-automated methods have been produced. Reisner et al. Lays out an objective method as opposed to subjective that allows the data to constrain 3D fault surfaces. So Plesch and others in 2020 did this for the Ridgecrest sequence. And that is how the CFM now has this complicated Ridgecrest structure that's based on an objective method that is semi-automated based on focal mechanisms and hypocenter locations. Another challenge of the CFM is metadata and file management. This is a big model, which historically was built by hand. So for all of our 440 preferred objects, there's a spreadsheet that has 24 columns of metadata. This is things like strike and dip and fault area, references, stuff like that. All of these faults are also provided in 4 different resolutions, along with fault traces in 3 different file formats, along with a reference document. This is a lot of stuff to manage. And if you're going to deliver this in an online environment, everything has to be correct, no inconsistencies. Why do we deliver 4 different resolutions? Well, this is the native mesh of the Northridge thrust. That's the hypocenter from 1994. And this outline shows the relocated aftershocks of Carena and Suppy. So the native mesh shows users where the data is from dense triangles out here where the triangles are sparse because there's very little data. This outer part is based on a dislocation model from Hudnut and others. This is the regularized surface that we provide to aid modelers to give them something that's more consistent element size. This is the 500 meter mesh. We also provide 1,000 and 2,000 meter meshes. So I hope this will help with modelers using these surfaces. So how have we responded to this huge amount of data that we need to manage? Well, we've written a series of scripts that checks the CFM for consistency. And yes, this is the best visualization I could think of. So let me show it to you. This is my terminal window. And what I did is I wrote a script that goes through the model and checks. It not only calculates all of these metadata parameters like strike and dip and total area and whether it's blind or surface breaching, and automatically updates the metadata in the spreadsheet. So if a surface gets updated, the metadata gets updated easily. It also checks all of the various files to make sure they're named correctly based on the hierarchical naming scheme. So one of my most exciting days ever was when this thing ran, and you'll see it in a second here. It gets to the end and says, no inconsistencies found. Woohoo! I was so excited. My daughter walked by and she's like, Daddy, why are you cheering? I said, don't worry about it. It's scripting. She's like, okay, and walks off. But because this was built by hand, you can imagine there were lots of minor inconsistencies, which are now resolved. These are not major. Any human could have recognized these things, but in a system that everything has to be perfect. So how do we deal with file formats? How do we even deliver this model? Well, long before I came along, the CFM group decided to deliver the CFM as GoCAD TSURF files. We want the software to be, the format to be non-proprietary and non-binary. That way people can use whatever software they want, and they can use scripting or editing to just simply edit the data as they need. So why did they choose this? I think this was a great idea. Get it? Light bulb? Great idea? Okay. So why is this a great idea? Let me show you. GoCAD files might sound proprietary because GoCAD is not free, but GoCAD files are open source. They're plain text. So this is 3 random triangles from the Northridge thrust: vertex 1, vertex 2, and vertex 3. Vertex 1 has X, Y, and Z coordinates in UTM. And then the triangle is formed by connecting vertex 1 to vertex 2 to vertex 3. That's basically all you need to define a surface. And that's more or less the content of a GoCAD file. So even if you don't have GoCAD, you can still use these files. And if you need it in some other format, please let us know. We might be able to help you with a script to convert it to whatever your needs are. We already provide several conversion scripts on the CFM homepage, so we hope those are useful. Next challenge is CAD software. If you're going to work with the CFM and model, you probably need access to some computer-aided drafting software. Here's the most common stuff that people use, and from my experience. Many of these are not free, and the ones that are free often require complex license negotiations. Some of you may know. So this is a view of the CFM and GoCAD. You can only see this if you have GoCAD. So what are we going to do to get more people to use the CFM? Well, what we've done is we've developed web-based tools along with the SCEC IT and software group. And these tools allow anybody that has a web browser and an internet connection, or even a phone or a tablet, to view the community fault model in map view, and as you'll see in a minute, in 3D, which is really cool. So I encourage you to check out these web tools. They're amazing. First thing I do when I go there is I load the relocated seismicity, which if you click on that button, you'll be greeted with the progress bar. Be patient. This is 1.6 million events we have to load. It takes about a minute. After it loads, you'll see the Hawkson et al. Catalog, the relocated seismicity catalog, shaded by depth. You can also shade it by magnitude or time. And in the pull-down menu, there's also an option to load the Ross et al. Catalog. You can change the background. Here is aerial photos. And let's zoom in on this area down here. near the Silmar event in 71 and the Northridge event in 94. Look at all this seismicity. Look at all the faults. What fault is this seismicity on? It'd be nice if we could see this in 3D. So what you do in the 2D viewer is you just click on the faults that you want. We made the initial viewer 2D just because it's easier to browse and you can see maps and stuff. But once you do this, if you click on the plot 3D, cool stuff happens. So this is a video. Here I've loaded it, clicked on it, and I'm going to click on the plot 3D option over here. You'll see I've selected the 1,000-meter regularized mesh. Please read this window. It tells you how to drive and navigate in 3D. Here I am turning off the bounds just to clean up the plot a little bit, and loaded the Hodgson et al. Catalog in 3D. And here I am gliding through the data in 3 dimensions with no specialized software at all, only in a web browser. You can clearly see that this seismicity is located in the hanging wall of the Northridge thrust, which is over here. There's a legend to tell you which fault is which. And you can even change the colors of the faults as you go. But it's pretty amazing to be able to do this right in a web browser with no CAD software. So if you want to browse the model quickly, it's there for you to do that. Well, the other challenge we have is CXM is the community models. What does community mean? Well, it means something different for each individual model. But for us, what it means is that the SCEC community needs to come together to evaluate this model periodically. So Anna at Harvard has built this really fantastic web interface that we're going to utilize for the upcoming CFM 5.3 evaluation. Late fall, early winter is when we're going to do this. It will have pictures of the major alternatives and information about what that's based on, and users can rank these. So we hope that everybody will participate in this evaluation as it's critical to the formation of the next CFM version. What's the future hold? Well, this is the current view of CFM 5.3, and in black is the USURF model. What we would like to see in the future is for the community fault model to spread to the entire San Andreas plate boundary, maybe something equivalent to the USURF focus. There is a preliminary state model available, but it's preliminary, and there's going to be a lot of data wrangling involved in getting this all in the same format and getting all the metadata. So this is a large effort, but this is definitely possible with the right focus and support. So we hope that the community fault model can grow to the entire plate boundary. We're also looking forward to creating a web-based form to assist users that want to submit new CFM faults. So that's what we're looking forward to the future. I hope you've enjoyed this tour and progress on this community fault model. And if you have any questions, I'd be happy to entertain them. Thank you very much.